Welcome to Unit 2 of our Explainable AI series. In this session, we are going to review white box and black box models and explore the methods available for making their decision understandable. For most of the topics, such as decision trees, linear models, and post-house explanation methods, we will take a broad conceptual overview to understand how they fit into the explainability landscape. But for one method, SHAP, we will take a deeper dive. It is one of the most widely used tools for interpreting black box models. So in this unit, we will explore not only how it works, but also the mathematical foundation behind it. Think of this unit as a bridge. We will begin with white box and black box models, move through different explanation methods, and then focus on SHAP to understand it in detail. On this slide, we see two boxes. On the left, the transparent box represents a white box model. We can see inside. It is open, clear, and gives us a sense of how it works. On the right, the black box represents a black model. We cannot see what is happening inside, and the decision-making process is hidden. This is the core challenges in AI. Black box models are often powerful, but hard to trust, while white box models are more transparent, but not always simple to understand. That is why we need explainability to open up the black box and make AI decision more understandable and trustworthy. When we talk about white box models like decision trees, we often assume they don't need explanation because they are already transparent. But in reality, that is not always true. A small decision tree with just few nodes is easy to follow, but a very large tree with many branches quickly becomes overwhelming, even though it is technically transparent. So the key point here is transparency alone is not enough. We still need clear explanation to make models understandable and trustworthy. This slide represents the two perspectives in Explainable AI. On the left, we see the crowd, the global behavior of the model across all data. This is like asking what patterns generally drive predictions. On the right, we zoom in on the individual. One specific prediction for one specific instance. This is the local explanation. Why did the model make this decision here? Both perspectives are essential. Global explanation shows the overall logic of the model, while local explanation builds trust case by case. Together, they give us the full picture of how AI systems behave. This slide is about model-specific XAI techniques. These are methods designed for particular model types. For example, decision trees are interpretable by design. We can directly follow the branch to see how features lead to a prediction. On the other hand, for the deep learning models, specifically transformer models, we often use attention mechanisms. The attention map here highlights which symptoms were most important in the prediction, the common core. So depending on the models, we apply different explanation techniques. This slide shows model-agnostic explanation. Unlike model-specific methods, these techniques work with any type of model, whether it is a decision tree, a random forest, or deep neural network. Here I am showing the Shapley additive explanations. SHAP is based on game theory and explains how much each feature contributes to a model's predictions. The big advantages of model-agnostic method is that they provide a common framework for explanation across different models. This makes them very flexible and widely used in practice. So, to summarize, model-specific methods are tied to a particular model type. Model-agnostic methods like SHAP can explain any model, giving us a consistent way to interpret complex systems. Here we come to SHAP, Shapley additive explanations. On the left, you see the original paper, which introduced the SHAP as a unified framework for interpreting model predictions. It is one of the most cited works in explainable AI. On the right, you see how the Chef Python library brings the idea into practice. It's assigned a contribution score to each feature, showing whether a feature pushed the prediction higher or lower. For example, in the case, each contributes positively while such contributes negatively. In short, Chef provides both the theory and the tools, a solid foundation from game theory, and an easy to use Python package for the practical model explanation. Let's start with a simple analogy. Imagine we have a project where multiple people contribute, player 1, player 2, player 3, and so on. At the end of the project, there's a payout or reward. The challenge is, how do we fairly distribute that payout among the players? Some might have contributed more, some might less. Sheffield value from game theory gives us a systematic way of fairly divide this payout based on each player contributions. This is the foundation of how Sheffield values work. Now let's connect this to machine learning. In black box model, each feature like age, gender, or BMI is just like one of those players. Instead of working on a project, their contribution to the model's predictions. The prediction itself is like the payout. Sheffield values break down the predictions and see exactly how much each feature contributes in an unbiased and consistent way. This makes it possible to explain even very complex models. Now, how do we actually calculate Sheffield values? The key idea is to look at all possible collisions or groups of features. For example, if we want to know the contribution of age, we don't just look at age by itself. We consider every possible way age can join with other features, like genders or BMI. We calculate the difference in the model's prediction when age is included versus when it is not, across all these combinations. Finally, we take the average of these differences. The average is the Sheffield value for age. In short, Sheffield values measure a feature contribution by fairly distributing the credits across all the possible feature combinations. On this slide, I want to explain how Sheffield values are actually computed and why this became challenging. The business idea is that for each feature, like age or VMI, we need to evaluate its contribution by looking at all possible subsets of features, what we call correlations. Each feature can either be included or excluded. So if we have m features, there's a 2 power m possible subsets to check. For a simple case with 10 features, there's already 2 power 10 equal to 1024 subsets. And as the number of features grows, this number explodes exponentially. This is why computing excess Sheffield value is very expensive in practice. To address this, Shep provides efficient implementations. Shep is a model agnostic method that works for any model by approximating this value. 3Shep is optimized for decision tree based on model likes XGBoost or random forest, making it much faster. DeepShed is designed for deep learning model, combining Sheffield principle with backpropagation. This is an example of shared feature important for predictions. Each bar represents how much a feature contributes to pushing the prediction higher or lower. Here we see that each has the largest contribution, followed by relationship and the capital gains. Feature like Marcia stated, occupations and hours per week also plays important roles. What this is there is about is not just the ranking of the feature, but the actual magnitude of their input on model output. This is one of the key strengths of the SHAP, is provide both global understanding and look at instant level of explanations. This is a SHAP summary plot. Each point represents a single data instance, showing how much a feature pushed the prediction up or down. The color represents the feature value, red means height value of the feature, and blue means low values. For example, higher H value, red, tend to push the prediction higher, while lower H value blue pushes lower. Similarly, capital gain shows a strong positive effect for higher values. This visualization combines two things: feature importance and the direction of their influence, giving us a much richer picture of how the model makes decisions. Here we see how Shep can explain individual predictions using what is called a force block. We start from the base value, that is the average prediction of the model over the entire dataset. Then each feature pushes the prediction either higher, shown in red, or lower, shown in blue. In the first example, at the top, features like occupations, hours per week, and education levels are pushing the output higher. On the other hand, age and relationship status are pulling the output lower. The final prediction begins 0.64. This way, Shep makes it clear not just what the model predicted, but why it is predicted the value by showing the takeover between the features. Shep isn't limited to the tabular data. It can also explain predictions in computer vision. Here, the color overlays show which regions of the image influence the model decisions. Red areas push the prediction higher, supporting the chosen class. Blue area push the prediction lower, arguing against it. For example, in the speedboat image, the highlighted regions around the speedboat show the features the model used more strongly. This allows us to peek inside what the model sees when making its decisions, turning a black box CNN into something interpretable. To wrap up, today we explored the difference between white box and black box models and explainable AI methods like SHAP. The key takeaway is that the explanation techniques allow us to see not just the predictions, but the reasoning behind them. This makes model more transparent, trustworthy, and practical in real-world use. As a next step, I encourage you to also explore the other approaches like LIME. I strongly suggest this book, Interpretable Machine, is great resources for learning how to make black box model more transparent and understandable. Thank you for your attention. If you have any questions, please feel free to contact me at g.dar@mion.se.